So the topic of this lecture is called the damped-driven harmonic oscillator. So we're adding another layer of complexity on top of our harmonic oscillator, and you might hear the word, in textbooks you might hear it referred to as the forced harmonic oscillator. So it's a harmonic oscillator which has an additional external force acting on it. And that force could be any kind of external force which is jostling it, causing it to, disturbing it a little bit. So what I want to do is introduce that system, which is called the damped-driven harmonic oscillator. And we'll see that this is a physical application of the techniques of solving ordinary differential equations, which are inhomogeneous. So we're seeing a physical context of the math that we talked about in the previous lecture. We're going to be in particular very interested in jostling the harmonic oscillator with a periodic force, so that's like a cosine or a sine. And this leads to something very interesting, which is called the phenomenon of resonance, which is incredibly important. There's countless applications of this that I can think of, like if you're building a building, you need to worry about this. Microwaves work on the principle of resonance. MRI, that's magnetic resonance imaging, so in some sense the resonance phenomenon I'm talking about here is related to that. Tons of applications, very, very important. The textbook that I'm using to base this lecture on is not our usual one, but is this book by French, which I think is really great. And so that's where you can find some more details on where this lecture came from. So let me introduce this system. This is the damped-driven harmonic oscillator. So what do I mean by that? Let's go back to the mass on the spring, which we've talked about many times. Mass m, spring constant k, is allowed to oscillate back and forth on a frictionless surface. And then recently we talked about what happens if you add a drag force to this. So that allows the damping, the oscillation to be damped out, and gives us the underdamped, overdamped, and critically damped solutions. So all I'm going to do now is add an additional force. So I'm going to call it Fd of t. So that's what I call the driving force. And it's just some external force, which could depend on time. So it's something else which is touching this harmonic oscillator, which is jostling it in addition to what its spring and its drag force. And that force could have many physical origins. It could be like the wind blowing, causing this thing, disturbing it a little bit. It could be a person pushing on it with some time-dependent force. Anything that's interacting with this oscillator and causing it, sort of disturbing it with some external force, we're calling it a driving force. So now when I write down the equations of motion, F equals ma, I have now an additional force. So my forces, as before, I had kx minus bv, which was the drag force, plus what I'm calling now my driving force, Fd, which depends on time, is equal to ma. And we can write this now mx double dot, so the a is x double dot, putting all the x's on one side, plus bx dot, plus kx, is equal to my driving force, Fd, as a function of t. And then, like before, we divided everything by m, so I ended up with x double dot plus gamma x dot plus omega 0 squared x. This is what we had before. And now I've got 1 over m, because I divided both sides by m, times Fd of t. So this is gamma is b over m. B is the drag force coefficient, and omega 0 squared is k over m. So the stuff on this side is stuff we've discussed before. That's the damped harmonic oscillator. And now I've got this new piece on the right-hand side. This is the driving term. So that's the new piece which we've added now. The left-hand side is exactly the same as it's just the damped harmonic oscillator. The right-hand side is a driving term. And you can see that this term is inhomogeneous. It makes the equation inhomogeneous. Previously, that term was equal to 0, and then I had a homogeneous ordinary differential equation, but now I've got something which is non-zero over there, so I have an inhomogeneous equation. So we need to use the techniques for solving inhomogeneous equations to solve this one. So our focus going forward in this lecture is going to be on periodic driving forces. So that's a driving force, Fd of t, which oscillates with time. So it's going to be some amplitude, F0, times cosine of omega d times t. And omega d is some, what I call a driving frequency. So I'm jostling this harmonic oscillator with some pulsing or oscillating force. I'm pushing it at some frequency. That frequency can be whatever I want, so that's something that I choose. It doesn't have to be related to the way this thing oscillates. It could be any frequency. Okay, so I call it a driving frequency, a different variable than the oscillation of the mass. So let me try to walk you through help you visualize what's going on. This figure on the left here is a little hard to see, but this inside this fluid is the mass, and it's like underwater in some fluid, so there's a pretty big damping force there. It's connected to a spring, which you can see is here. So if that was it, you know, if I just had this attached to the ceiling or something, I would have a damped harmonic oscillator. I would joscillate it up and down, and the oscillations would damp out. But instead I've got it attached all the way through this string over to this turntable, which is turning around. And that turntable is causing that string to move up and down with some frequency, which I'm calling omega d. So I'm jostling this thing up and down with some frequency which I can control using this turntable. And I can also control the amplitude of that oscillation if I made this little thing bigger or smaller. So that's the idea. So I jostle it, I can control the frequency at which I'm jostling it and the amplitude at which I'm jostling it. And I want to know what happens to the system as time goes on. Here's a visualization to help you visualize what's going on if it was all on a line. So I've got here my turntable turning around. That's jostling one end of the spring with a periodic force, and then the mass is responding to that. And you can see that the motion can be quite complicated as this goes on. So what I can control is the amplitude of the driving force, which I'm calling F0. F0. And how I can control that is I can make this kind of wheel or turntable bigger or smaller. So if I made that bigger, then this thing, maybe it's better to draw it something like, if I drew it like a bigger wheel, then this end would oscillate back and forth bigger. And if I made it a smaller wheel, the end would oscillate back and forth with a smaller amount. So I can control the amplitude of the driving force by, it's related to the radius of the wheel controls this. Okay. And then I can also control the frequency of the driving force, which I'm calling omega d. And that I control just by how fast this thing goes around. If I make it go faster around, then this thing oscillates back and forth faster and faster. So I can control that as well. The other inputs that I need are B, the damping coefficient, the mass, and K. And I can remove these instead of B, M, and K. I can just use gamma for the damping and omega 0 for the natural frequency of the mass on the spring. So my solution is going to depend on all these things, and my ultimate goal is to know what is the mass doing as a function of time, x of t, in terms of all of these variables? That's what we're after. Okay, so let's get working on it. So again, here's my system. Those are the forces acting on the system, and we were able, in the very first or second slide here, we were able to get the ODE describing this, which was x double dot plus gamma x dot plus omega 0 squared x is equal to the driving force, which now we're saying is a periodic, a cosine driving force. Cosine omega d times t. And omega d is some driving frequency, so be very careful. This omega d is not the same as omega 0, right? It's something independent. I can drive it at any frequency I want to, so it's not necessarily the same as omega 0. Okay, so that's an inhomogeneous equation. And we know how to solve this. The first step is to solve the homogeneous equation. Find two solutions, x1 of t and x2 of t. And we've already done that. We know how to do this already because we talked extensively about the damped harmonic oscillator. This is just the damped harmonic oscillator. That's where there's no driving force, right? Where the right-hand side here is equal to 0. So if that side is equal to 0, I have the homogeneous equation, and I just have my usual damped harmonic oscillator. So I won't write them out here. I will write them out later, just to save time and space. And then once the second step is to find the particular solution, xp of t. And once we have that, we have our general solution, which is x of t is you add the homogeneous solutions with arbitrary constants, and then you add the particular solution. So this we already know, and this is our main target. We need to figure out what is a particular solution to this ODE. So that's what we need to focus on. Once we know that particular solution, we know everything about the system, and we can write down the general solution.